welcome you to this video series on quantum mechanics. Today we are going to discuss about linear independent sets and basis. The outline of today's course is we are going to discuss first about what is linear combinations of vectors, what is linearly independent vectors, what are the dimension of vector spaces, what is basis, and is this basis unique, and how we can represent vectors in terms of some basis sets of vectors. Then I will be giving you some problem to ponder upon. So let's begin. So let's start our discussion with linear combinations of vectors. Whatever we are going to discuss today, we are going to consider that it is established that whatever set of vectors and set of scalars we are going to consider, they form a vector space. And based on that particular assumptions, we are going to do the mathematics. So in case of linear combination, if I can write something like this, suppose I have a scalar A, I multiplied that scalar by a vector, let's say alpha 1, plus a scalar B multiplied by vector alpha 2 plus scalar C multiplied by vectors alpha 3. Such a combinations of scalars and vectors is known as linear combinations of vectors. So these vectors alpha 1, alpha 2 and alpha 3, they are linearly combined together to form, obviously to form some vector. Let me call it as some vector chi. And as you know, the vector addition is closure. What I mean by closure is that by adding two vectors, you will get the vector from the same set. This also belongs to the same set of vector space. So that's about linear combination. Based on this linear combination, now we are going to discuss about what is known as linear independent set of vectors. So if I take a set of vectors, let's say alpha 1, alpha 2, alpha 3. So I'm going to take a set of vectors, let's say alpha i's from our vector space. It is a subset of vector space. Then this set of or subset of vectors alpha i's are said to be linearly independent if and only if this condition is getting satisfied. Summation over I ai alpha I is equal to 0 if and only if ai is equal to 0. So the linear combinations of these vectors from this subset will be equal to 0 if and only if all the coefficients that I am going to represent is equal to 0. What does that mean? It means that no vector from this particular subset can be represented as a linear combination of all other vectors. If it could, then without having ai is equal to 0, I can have this particular relation equal to 0. Let me take an example. Suppose this is my subset of vectors. Now can I represent this particular vector? Let's say alpha 1, this is alpha 1, this is alpha 2, this is alpha 3. Can I represent either alpha 1 as a linear combination of alpha 2 and alpha 3? Or can I represent alpha 2 as a linear combination of alpha 1 and alpha 3? Can I represent, let's say, alpha 3 as a linear combination of alpha 1 and alpha 2? No, it's not possible. If a vector from a set cannot be represented as a linear combination of other vectors from the set, the vectors are said to be linearly independent. Now look at this particular condition. Does this particular condition get satisfied? Yes, obviously yes. If I have a linear combinations of alpha 1 plus alpha 2 and alpha 3, the linear combination will be 0 if and only if all the coefficients of this particular vector and this particular vector and this particular vector is equal to 0. So this set is linearly independent set. What about this? If I add, let's say, alpha 4, which is 3, 2, 1 and 0. So I have 4 vectors now, alpha 1, alpha 2, alpha 3 and alpha 4. Is this particular set of vectors linearly independent? No, because I can represent alpha 4 in terms of alpha 1, alpha 2 and alpha 3. So I can write something like this. I can write alpha 4 is equal to 3 alpha 2 plus 2 alpha 1 plus alpha 3. So I can write alpha 4 in terms of alpha 2, alpha 1 and alpha 3. So this is not linearly independent set of vectors. Can I have only single set of linearly independent vectors? No, I can have large numbers of linearly independent set of vectors. As an example of 2 by 2 matrices, I can have some sets like this. So as you can see, I can have many sets of linearly independent vector. This is linearly independent set of vector. This is another linearly independent set of vector. This is another linearly independent set of vector. So the sets of linearly independent vector is not unique. We can have more than one linearly independent set of vectors. Does the linearly independent set of vectors have the same numbers of vector in it? No. Look over here. This particular set, which is linearly independent, have 3 vectors. Over here, there are 4 vectors. Over here, there are 4 vectors. I could have only 2 vectors. Let's say 1, 0, 0, 0, 0, 1, 0, 0. This set will have only 2 vectors and it is linearly independent. So it's not required that all the linearly independent set should have the same numbers of vectors. That's not required. Let's start with span of the vector space. Now suppose I have a subset of vectors. If all the vectors in a vector space can be represented as linear combination, these vectors, then this set of vector is said to span a vector space. What does that mean? It means that if I have a set of alpha i's, using those alpha i's, if alpha i's span the vector space, using these alpha i's, I can represent any vector in a vector space. How I'm going to represent any vector in a vector space? By using linear combinations of this alpha i's. Next thing that we are going to discuss is basis set. Basis is defined as a set of maximum number of linearly independent vectors that spans the vector space. What does that mean? It means that basis is a set of linearly independent set of vectors, and using this set of vectors, I can represent any vector in a vector space by using a linear combination of these vectors from basis. So, suppose I have some vector, I have some set of basis vector. Let's say I have alpha 1, alpha 2, up to, let's say, alpha n. So I have n number of linearly independent vectors, and these vectors also span the vector space. And suppose I have some vector A from a vector space, then I can write something like this. So I can represent a vector A from a vector space as a1 alpha 1 plus a2 alpha 2 plus a3 alpha 3, so on and so forth, plus an alpha n. So I can represent a vector A in terms of linear combinations of these basis sets. Isn't that what we do in our Euclidean space? In our Euclidean space, we represent any vector in terms of I, j, and k. So basically, these for Euclidean space, you can represent any vector in a Euclidean space using I cap, j cap, and k cap. How you represent them? You represent them by a1i plus a2j plus a3k. Similarly, over here in n-dimensional vector space, we haven't discussed about the dimension of vector space, but in n-dimensional vector space, we are going to represent a vector as a linear combination. So these coefficients a1, a2 up to an, they are similar to our components of I, j, and k. How we represent our Euclidean vector space? Suppose I have a vector in Euclidean space, let's say vector A, we say that it will be a1 I cap plus a2 j cap plus a3 k cap, and we simply represent A by this coefficient a1, a2, a3. Like, isn't it? Similarly, over here as well, a vector in a vector space is represented as linear combinations of these basis sets alpha 1, alpha 2, alpha 3, up to alpha n. So I can represent this vector in vector space A just by this coefficient a1, a2 up to an. Now this representation is very helpful, as in our Euclidean space, if we want to add two vectors, let's say vector A plus vector B, what we do? We just add their components A1 plus B1 A2 plus v2, a3 plus a3. Correct? Correct? Similarly, over here also, in order to add two vectors from a vector space, let's say you want to add vector a plus vector b, you will simply need to add their components a1 plus b1, a2 plus b2 up to an plus bn. If you want to multiply a vector, let's say some vector a with a scalar c, then it will be simply multiply each component by c, c a1, c a2, c a3 up to c a n. A null vector is just a series of n zeros. And an inverse vector minus a will simply be minus of all components. Compare it with our Euclidean space and it will help you understand this particular concept. We will be discussing more about representation of vectors using the components. If I have defined a basis, then in that particular basis I can represent a vector in terms of its components, something like this, or rather something like this. This is defined under a basis. A particular basis. Please note that the choice of basis is not unique. The choice of basis is not unique. Because of that, if I am working under some basis and somebody is working under some another basis on the same vector space, then my representation will look weird to somebody else and somebody else representation will look weird to me, even though we both are working on the same set of vectors or the same vector space. That is the only disadvantage of this particular method. But it's very powerful because it saves a lot of mathematics. Our mathematics is limited only to addition and subtraction of numbers or components. Let us quickly discuss about what is dimension of a vector space, and then we will look into this particular concept using some examples. Dimension of a vector space is defined as maximum number of basis vectors the space can have. Just before I have said that the choice of basis is not unique, and now I am saying that dimension is defined as maximum number of basis vector. So does it mean the number of basis vector in any basis set is same? Yes, this is the number of vectors, basis vectors in any basis set is equal. So suppose I am working on some basis set and somebody else is working on a basis set. So if I have 10 basis vectors, somebody else will also have 10 basis vectors. One more thing, can the basis set is finite only? No, you can have infinite number of basis vectors. That particular vector space will have infinite dimensions. We have covered a lot today. Let's summarize it and then we will discuss it using some examples. Linear combination of vectors. Then we discuss about linearly independent set of vectors. Then we discuss about span and basis set. So let's summarize it. What is linear combinations of vector? Linear combinations of vector is nothing but you combine the vectors and scalar linearly to represent another vector. What is linearly independent set of vectors? If you form a set and from that set you cannot represent any other vector as linear combinations of the other vectors, then that set is called as linearly independent set of vectors. What is span? If I have a set of vectors and any vector from a vector space can be represented as a linear combination of that particular set, then that set is said to span the vector space. What is basis set? Basis set is a set of linearly independent vectors which span the vector space. There could be large numbers of linearly independent vector set and there could be a large number of basis sets. In linearly independent vector set, the number of vectors may or may not be same. However, in case of basis set, if I have let's say 2 or 3 basis sets, in all the basis sets, the number of vectors will be same. Please note I am saying the number of vectors, not the vector. It will be clear in a minute. So let's discuss about this particular concept. So we have discussed about what is linear combinations of vector using example. We have also discussed about linearly independent sets of vectors. Let's again discuss linearly independent set of vectors. I will be discussing this concept using a 2 by 2 matrix. Our vector space uses of 2 by 2 matrices. Out of these, now suppose I choose some vector like this. Suppose I have a vector C1. So I have this particular set of vectors from 2 by 2 matrix set, 2 by 2 matrix vector space. Now, is this vector linearly independent? No, they are not. Why? Because this I can represent as linear combination of this vector and this vector. So let me call them by some name. So this is my alpha 1, alpha 2, alpha 3, alpha 4 and alpha 5. So these are not linearly independent. Linearly dependent set of vectors. But this set will span the entire vector space. It will span the vector space. How? Let's take an example. Suppose I take a vector from this vector space, something like this. I can write it as 3 times alpha 5 plus 2 times alpha 4 plus alpha 3. I can represent this matrix 3 3 2 1 as 3 times alpha 5 plus 2 point alpha 4 plus alpha 3, or this can also be represented as 3 times alpha 1 plus 3 times alpha 2 plus 2 times alpha 4 plus alpha 3. I can take any vector from 2 by 2 matrices, and this, using these vectors, I can represent that vector. I can represent that vector I have chosen using these linear combinations of these vectors. So hence it proves that this linearly dependent set of vectors span the vector space. For span, it's not required that the set of vector is linearly independent. A dependent set can also span a vector space. Now let's talk about example of basis. So let me just tick it out. So we have discussed about example, we have discussed span. So we will be discussing using the same 2 by 2 matrices. So the requirement for basis is that the first requirement is the set should be linearly independent. And the second requirement is it should span the vector set. Yes. Now let me take this particular set of vectors. Let's say I have chosen 3 vectors. So 1 0 0 0 0 1 0 0 0 0 1 0. These are the 3 vectors. Are they linearly independent? Yes. I cannot represent this as a linear combination of this, or I cannot represent any vector from this particular set as a linear combination of rest of the vectors. So these are linearly independent. But can it span the vector space? No, it cannot span the vector space. For example, if I want to represent this, I cannot represent that using this, because in order to represent this one, I could not represent this one using this vector, right? So this is linearly independent, but it does not span a vector space. So does it form a basis? No, it could not form a basis. However, if I write this particular thing, now is it linearly independent? Yes. it is still linearly independent. Does it span the vector space? Yes. Now I can represent any vector in a vector space using linear combinations of these vectors. So this also spans the vector space. So this forms a basis. Right? Now, is this choice of basis unique? Can I think of some other basis set? Yes, obviously. The choice of basis is not unique. Somebody can say that, okay, instead of saying using this, I can use this. So this is another example of linearly independent vectors. Are these linearly independent? Yes, obviously yes. But can they span the vector space? Let's take an example. Suppose I want to find out whether this vector can be represented in terms of this basis. Obviously, I can represent this as, if I call it as alpha 1, alpha 2, alpha 3, and alpha 4. That will be equal to, that is equal to, which is our initial matrix. Can I represent any other metric using this? Obviously yes. Instead of this, I can take anything you want. Random number 5, 1, 3, 2. So that will be, that will give me, which is equal to, which is our initial matrix. So this proves that the choice of basis vector is not unique. I can have more than one basis set. The representation in different bases are different. For example, the representation of this matrix in this basis will be, the components will be 5, 1, 3, 2. 5 alpha 1, 1 alpha 2, 3 alpha 3, and 2 alpha 4. On the other hand, with this basis, the the vector can be represented as 1 alpha 1, 2 alpha 2, alpha 3, 1 alpha 3, and 3 alpha 4. So the representation is different. In this basis, it is represented as 5, 1, 3, 2. Whereas in this particular basis, it will be represented as 1, 2, 1, 3. So you see the representation of matrix in different bases is different. Okay. Now what is the dimension of this particular 2 by 2 vector space? The dimension obviously is the number of basis vectors. So how many basis vectors do I have? 1, 2, 3, 4. So the dimension of the space will be 4 dimension. So this 2 by 2 vector space is 4-dimensional vector space. These are the problems that you need to solve in order to understand this basis and linearly independent vector space in more detail. These are also given in the description box. I have used this book in given order of references. Thank you for your time. Like the video. Do subscribe our channel. Your comments and suggestions are welcome. Thank you.